Hey guys, today I wanted to make a video just about binary search. Last week's LeetCode Daily topic was primarily binary search, and I did struggle quite a bit with a couple of these problems, which is why I want to make this video. If you're new to binary search and you don't really know what this is, I think this would be a great video. If you know how to implement binary search, but you're also struggling to how does it relate to certain problems, I think this video is good as well. Because I think I'm more in that category. Like I know how to implement binary search, but then all of a sudden I'm reading these problems and I don't even think to use binary search. So that's why I want to make this video. We're going to talk about what binary search is, how to implement binary search. Then we're going to look at two direct problems where the question or the problem pretty much asks you to use binary search. And then we're going to look at two indirect problems where the question doesn't say anything about binary search and it's not obvious that you have to use binary search. Then lastly, I'm just going to tell you guys how I identify these binary search type problems. So without further ado, let's start the video. Okay, so the first part of this video is talking about what is binary search. So at its core, binary search is a searching algorithm, right? So it's a searching algorithm for sorted arrays. And that's very important. We'll see like the array needs to be sorted for binary search to work. Okay, what can we do with binary search? Well, we could find something, right? Like if they want us to find an element in the array, like 7, they could ask us, hey, does 7 exist in this array? We can use binary search to find if 7 exists in the array. We can use binary search to find what index 7 is at in the array. So it would return 4. And we could also do like a little guessing game. So I'll start with just like finding, right? If you told anyone to just find a 7 in the array, I think most people would start from the beginning and just move all the way to the left, checking each index to see whether that element is equal to 7. Now, if we were to do that, that's okay, right? That would be a linear search. What's cool about binary search is that it actually runs in better than linear search time, which is log n. And this is how it does that. So we will be looking primarily at these indices. So what I have in blue over here are indices, right, of the array. So 0 to 5, there are 6 elements. Now, if we want to find a 7, what we do is we just take the left, take the right, and divide it by 2. So 5 divided by 2 is 2. So we kind of just find like a middle. That's the whole point, right? So this is our left, this is our right, and the middle would be a 2. Now what binary search does is says, hey, now let's process this middle. Is this a 7? It's not a 7. So it's a 4, which is smaller than a 7. And since we know that binary search works on sorted arrays, we know that this array is sorted, we know that the 7 now has to exist somewhere here, right? It can no longer exist in the left side because that's everything less than 4. So with that being said, we could kind of just cross this part out. Furthermore, we can move left over here. So now left is at 3. And now we're just going to search between left and right, which means we need to update our middle to be 3 plus 5, which is 8 divided by 2. So it's 4. And let me just write that more explicitly, right? The middle is just going to be like the left plus the right divided by 2. So in this case, it's going to be 3 plus 5 over 2, which is 8 divided by 2, which is 4, which is exactly why I'm putting middle at 4. Okay, so now we're going to process the middle, same thing. And we just check, hey, is the value 7? It is, so we return true. So now you see, instead of checking every single element in the array, we only made 2 checks, just so we were more efficient, right? So instead of O of n, we actually were able to find this and in log n time. So that's kind of the reason why we use binary search. And once we found this, we could return a true, whether it exists. We could return the 4 because that's the index. We could do many things, right? Yeah, I guess so. That's that part of the video. This is binary search. Now let's get to implementing binary search. Okay, so now let's go to actually implementing a binary search in code. I do want to run through a couple problems. We're going to start with a very standard basic problem. It's literally called binary search. And over here, I drew out the first example. The whole problem is just we are given this array. We're also given a target value, and they want us to find the target value in the array and return the index of where that target value exists. So just visually, right, we see that 9 exists. So what we would return is a 4. That would be our result, right? And that's our output is a 4. So yeah, let's just get right into this. So like I did in my example before, we definitely need a left and right, and these are just going to be the extremes of the array. So I think one thing that's really good is always just have some sort of variable that holds the length of the array. And for me, I just named that n. So then we can assign left and right. So left is going to be 0. And left is going to be 0. When I talk about left and right, these are going to be indices, right? These aren't the actual values of the array. These are the indices in the array. So left is going to be 0, right is going to be 5, which is n, because n is 6. That's the length of the array, minus 1. Cool. Now how binary search works is we just want to loop while left is less than equal to right. Let's do something. And that work includes finding a mid, right? So we have to find mid. And what mid is left plus right divided by 2. Now, some languages doing left plus right, if we just think of big picture, left could be something super big, right can be something super big as well. There's a possibility that this will actually overflow. So this is easy to understand, right? Left plus right divided by 2 is very easy to find mid, that makes sense. But how most people will actually rewrite this is left plus right minus left divided by 2. And now doing this avoids any sort of overflow. Of course, in Python, there is no overflow. You could just do left plus right over 2, but I'm going to start writing it like this. This is just best practice, I guess. So anyways, once we find mid, if we were to plug this formula in, it would be 0 plus 5 minus 0 divided by 2. And this is integer division. So 5 divided by 2 in integer division is just 2. So that's going to be our midpoint right here. So let's go ahead and process this mid. And what it means to process is to check if we've found our result. So if num's at mid, right, because mid is an index. So if num's at 2, which is 3, if it is equal to the target, then we're done, right? We just return, they want the index, so we return our index, which is mid. Okay, otherwise, there's only two things, right? Either nums at mid is less than the target, or nums at mid is greater than the target, right? So what happens if nums at mid is less than the target, which in this case it is, right? Because 3 is less than 9. Well, then we know that we could totally ignore this portion, this half of the search space, and all we need to do now is move our left over here. So what that means is our left is now equal to 1 plus whatever our mid is, mid plus 1, right? Okay, now what happens if, let's just say we want to find a target of 0 and we're at 3. Well, then we know that we could totally cross out the whole right portion. Then we can take right and move it to 1 minus the mid, or mid minus 1. But since that's not the case over here, we do mid plus 1 to be our left. And now since left is still less than or equal to right, and we haven't found our target, we're just going to keep searching. So the next loop, it's 3 and 5. So what's the middle of that is 4, right? So it's going to be here. Then we're just going to, again, process mid right here. Now we see that it is target, so we're just going to return mid. That's it, right? Now, doing this whole thing, if we never found target, the eventually left and right would just overlap, and actually left would cross over right, and this loop would break. Then we could just return -1, right? So let me go ahead and run this. Nice, that worked. And then I'll go ahead and submit just to make sure we didn't make any errors. Nice. Okay, that worked. So now I'm going to move on to the second problem. Okay, so for this next problem, for the direct part, we're going to do problem 34, find first and last position of element in sorted array. So the difference here, or the same part, is we're given an array and we're also given a target. The difference is that this array is still sorted, but it could contain duplicates. You see 7 appears twice, 8 appears twice. So now they're going to give us a target value. In this case, it's 8. And they want us to return the starting position as well as the ending position of that target. So if we look here, we see that 8 has a starting of 3 and an ending of 4. So what they want us to return is 3, 4. Keep in mind that 3 and 4, these are all the indices, right? These are all indices. With that being said, yeah, I think this is a very important problem, and it's new, right? It's not the same as the last one. The difference is these duplicates. So how are we going to do this? And also one more thing, if t was, let's just say a 9, and 9 never exists, well then they say just return -1. So that's another thing that we need to watch out for. Okay, so how I like to approach this problem is just by splitting it up into 2 parts, right? The first part is just to try to find the first occurrence of the left. And that could be a helper function, find first, which is going to take in some sort of target, right? And it's going to return the index of where it occurs. And keep in mind that this index could potentially be -1. So just like a regular binary search, let's go ahead and have our left and right pointers. But I want to start by saying n is the length of nums so that our left can be 0 and our right could be n-1. Now the difference about this is that instead of just jumping right into the while loop, I do want to kind of store some result that initially is -1. And this is the whole binary search, right? Below it is the whole actual like binary search implementation. If we never find the target, res would be unchanged at -1. We would just return -1, and that's perfect, right? Like if t was 9, we never found 9. After exiting this binary search, we just return -1. Sorry, we just return res, which is -1. Okay, so that's a slight difference, is now we're just going to keep track of our result. And here's the reason why. Let's kind of expand this out. If we had a bunch of 3s, let's just say, and it had a bunch of stuff before it, like a 2, and then maybe like a 5 over here, and it just went like this. And let's just say this is our mid right here. Oh, I drew that horrible. Let's just say that this is our mid. First, let's find the mid. Mid is left plus right minus left divided by 2. Now, if mid is the target, let's just say our target was 3. So if nums at mid is equal to target, that's a good thing. So let's put our result as mid. It could be this answer, but we know it's not going to be, right? We know that we could potentially do better. So we should look at the left, right? Because we want the first occurrence of 3. So now our search space is the left. What this means is that our right needs to be mid -1, right? And then after this, everything else is the same as the first binary search. Else if nums mid it could only be either less than target or greater than target. Now I'm running through this fast because this is the same as the previous one, right? If nums at mid is less than the target, we know that the target exists somewhere to the right. So we need to search to the right. Left is mid plus 1. Otherwise, we know that nums mid is greater than target, so our target's on the left. Let's search to the left. So right is mid minus 1. So this is finding the first occurrence. Similarly, let's find the last occurrence. Now, to find the last occurrence, I'm just going to copy this code because it's very similar. The only difference here is that once we found nums mid is equal to target, instead of looking to the left, this time we could scratch that and let's just search to the right to potentially find the last element. So the current element that we're on, yes, let's set that to result. But then instead of right being mid minus 1, let's have left be mid plus 1 because now we're going to search the right of the array. And you'll see that res just keeps getting updated. By the end of this loop, we guarantee that the last thing in res is going to be the index of the last element, right? So very similar. All we need to do now is just say left is find the first of target. Right is find the last occurrence of target. And then we just return an array, the indices left and right. Cool, so that ran. Let me go ahead and submit that. Nice, and that worked. So yeah, so we're slowly adding to our toolbox. We're seeing these new problems, but like I said, those were two direct problems. So it should be obvious that we have to use binary search. It might not be obvious of how to code it up, that's fine, but at least we know like, yeah, we have to use binary search. So the next part of the video, we're going to run through two indirect problems where it's not obvious that we use binary search. Okay, so now we are moving on to a couple indirect problems. And this is what I mean by indirect. Let's read the problem together. 2226, maximum candies allocated to K children. So you're given an array, candies, and each element in the array denotes a pile of candies. Like this is how many candies are in this pile, 5 candies, 8 candies, and 6 candies. You can divide each pile into any number of subpiles, but you cannot merge two piles together. And okay, you are also given an integer k. So k represents the number of children that you should allocate piles of candies to, such that each child gets the same number of candies. Right? So each child can be allocated candies from only one pile of candies, and some piles of candies may go unused. Okay, that's kind of confusing. What do they want? Return the maximum number of candies each child can get. Okay, so just by reading this, we know that k is the children, right? So if k is 3, that's we need to give 3 piles. We need to create 3 piles out of these piles of candies because we could even do subpiles, and we need to distribute them to the kids. Now, let's just say we created piles of 1, or yeah, piles of 1. So with 5 candies, we can make 5 piles, right? 1, 2, 3, 4, 5. If we had a pile of 8, we can make 8 subpiles. So it'd be 8 like this. And then if we had 6, we could do 6 as well. Then yeah, we could take 3 of those and give 1 candy to each child. So 1 works. But you see how they want the maximum number of candies. So 1 is definitely not the maximum. We can do better. So just this, like, I'm just explaining this problem, and I don't know about you guys, but to me, this originally does not seem like binary search at all, right? Let's look at what the solution is for the expected output for this though. It's a 5, right? Because we don't have to split this at all since there's 3 children and there's 3 piles. We just need to take probably like the minimum of this. So that's 5. We can make 5 here. This pile can split from 5 to 3. but we'll just keep the 5. And similarly, this can be a pile of 5, and then the remaining would be a pile of 1. That being said, we will just take these 3 and give them to the children. That's why 5 is the maximum number of candies that we can give to the children. Now, not even thinking of binary search, just look at one more example that I drew up. 8753 with a K of 4. Now, you might be thinking, okay, since we have 4 piles, let's just take the minimum of it. So, okay, our answer is 3. So 3 would definitely work, right? Because we could take 3 from here, we can take 3 from here, take 3 from here, take 3 from here, and now give them all to the 4 children. So 3 definitely works. But can we do better? How about 4, right? What if we did 4? Now, if we did 4, the 8 would split and give us 2 piles of 4. The 7 will give us a 4 and a 3, but we don't care about the 3. A 5 will give us a pile of 4 with another pile of 1. We don't care about that. And 3 just doesn't have enough candies to make a pile of 4. But that's okay, because look, here are all of the 4 piles that we can give to the 4 children. That being said, 4 works as well. So originally, I thought the answer might be 3, but in reality, it's 4. Okay. So now that we know what the problem expects, it's okay if you still don't know binary search, because I haven't even talked about binary search. And I wouldn't even think of binary search when I read something like this. But what I know for sure is that if they want the maximum number of candies, why don't I kind of have like a table, right? Why don't I have all of the like possible answers and whether they work or not? We can say start at the very base case, right? Does 1 work? Does 2 work? Does 3? And possible answers as in, can we just give each child 1 candy and be okay? Remember in the first problem, if we give 3 children 1 candy, we can definitely create 3 piles of 1 candy. So this would be true. Can we do that with 2? Yes, we can. That's true. Can we do 3 candies, right? 3, 3, 3. Yes, we can. So on and so forth. We could keep searching this and keep looking for the best. Now, when we go to 5, like the result was 5, right? So that's true. Now, let's look at 6 really quick for this 5, 8, 6. So 5, 8, 6, and we want a pile of 6. Well, 5 doesn't have enough to make a pile of 6, so we move to the next one. 8 can make 1 pile of 6 with another pile of 2, and then 6 will just make its own pile of 6. So you see how there's only 2 piles of 6 to give to 3 children? So that wouldn't work, right? This would now be false. So what this means is that anything to the right of it, like if we want a pile of 7 or a pile of 8, all the way to do as much as you want, we could guarantee that it will never be enough. If 6 wasn't enough, definitely 7 would not be enough. Definitely 8 will not be enough. Now, our whole goal here is to just kind of find maybe the last occurrence of where it was last true, right? Because that would be the maximum number of candies to give to children. Now, here's the cool part. Remember the problem that we did previously? Finding the last index? That's kind of similar to this problem here, right? It's similar in the fact that we have like all of the same value, like true, 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 and all of a sudden it goes false. So if we just want to find the the last occurrence of true, we can do that using binary search. Now, with that being said, I don't think knowing to use binary search right away is super intuitive, right? Like even if I told you this is how we would do it, I think most people again would just do a linear thing, right? Does 1 work? No. Does 2 work? Does 3 work? And we just keep going this way until we see the first false. Then we know the last true was 1 before it. And then we could just return. That would be linear O of n. But I think I think we're okay to just skip that. Like that would be in my opinion, that would be the intuitive way of doing it, right? But now let's actually talk, since this is a binary search problem. Oh, real quick, if you actually implement it that way, it wouldn't pass. It would get like time limit exceeded just because our constraints are so high. They're kind of hinting at a binary search solution. So with that being said, let's go ahead and code this up. So I don't really want to get into the details of this whole like, does the piles work? Just because this is just like a binary search video, not this maximum candies specifically. But in general, with these types of problems, it's good to have a helper function that says like, is it possible? Or like, does it work? And it will return a Boolean, right? Just like over here, we said, does 4 work? And it returns true. So what is 4? It's a possible answer, right? So and what is the possible answer? That's how many candies per pile. Candies per pile. Right, so then I can just have like a piles count. Then we can look linear in candies, and we could say like for candy and candies, how many piles can we create? We can create the number of candies divided by the piles per the candies per pile. That will give us how many piles we can get from the current candy. Now, after we do that for all of them, we just need to return whether those piles are greater than equal to the number of kids. If so, that means we can definitely give that many piles to this many kids. Sorry, then we can give this many kids those candies per pile. That's what it means, right? So now here is where we could actually implement binary search, trying to find the last occurrence of a true, right? And to do that, we just have left, right? Actually, so with these indirect problems, we're no longer, it's not really obvious what our bounds are, right? Like, we don't even know if left should be 0. In this case, left actually shouldn't be 0 because if we put candies per pile as 0 and we do divided by 0, we would get an error, right? So we actually want to start at left as 1. And if you think a little bit farther, that kind of makes sense, right? Because why would we create piles of 0? That doesn't make any sense. We'd have to give at least one candy in the pile to the kid. So our left bound is actually 1 this time, and our right bound, and this is very like problem specific, but this is a pretty hard part of these problems, is finding what are the bounds. So for this, maybe it could be like worst case, just give the maximum number of candies. It's just the max of the candies array. It's like, can we give 8? Can we give 8? Can we give 8? Because there's no way that we can ever give 9 like make a pile of 9, right? Like this wouldn't work, and this doesn't have enough. So I think it would just be the max of the candies. That's our left and right bound. So sorry, before I do the whole binary search, just like the last problem, we could have a result, and that result, it could be none in the beginning. Now we could do while left less than equal to right. Or actually, it could be 0, right? Because if it's not possible, like this, if it's not possible, they just want you to return 0. So I think we can go ahead and just put a result as 0. If it never gets touched, we'll just return that 0. Okay, now here is the binary search part. We start with a left and a right, which means we're going to get a mid of 4. So not a mid of 5. We're going to get a mid of 4. Which is mid right here. So we just need to process this like so. That means mid is left plus right minus left divided by 2. So all we need to do now, remember before we just said like the array at mid is equal to target? Well, now we want some sort of true and false thing, and we have a function that does that, right? We could just say if is possible at this mid, The potential answer of 4, was it possible? It was possible. So then let's go ahead and set our result to mid. But then let's look at the right portion, because maybe we could find something even better, right? Because if you recall, they want the maximum number of candies we can get. So even though 4 works, we need to check to the right, because maybe 5 or 6 or 7 works as well. Which means now our now that our left needs to be mid plus 1. And if it didn't work, let's just say we were like, if this was our mid and this didn't work, well, we know searching farther to the right will definitely not work. We have to look to the left, which means our right needs to be mid minus 1, right? So once we find the last occurrence of true, it's going to be in res. We would just return res. And if we never found something that was possible, we would just return 0. Right, so let me go ahead and run this. Cool, and then I'm going to submit. Awesome, that worked. That worked, right? And just really quick, we said that binary search is log n, but this problem isn't log n, right? It is log n in the fact that this while loop just will run log n times. But look, we're calling is possible every single iteration. So that's going to be log n times whatever time complexity this is. And for this, we're actually looping candies. So that's linear. So it's going to be an n log n time complexity, right? And that's just something to note. And actually, to be more specific, it's m log n, where m is the max candies. Cool, but that's kind of getting sidetracked. I just wanted to kind of bridge those indirect problems with, the direct problems with the indirect. And a tip that I can give you is when they want the maximum number of candies, we know that at some point it's not going to work, right? Like we can put 1 in, 2 in, 3, 4, 5, 6, 7. At some point, it's not going to work. And at that point is where we want to find our result. Okay, so if you made it to this point in the video, thanks for watching. We're just going to do one more example. And in my opinion, so I stumbled across this problem yesterday and I spent like 2 hours trying to do this. So I think even if you got a lot of practice with implementing binary search type problems, this one is tough. And the hard part about it is actually not the binary search side. It's more of that helper function that tells you, does this solution work, right? Like for the last one, remember it was is possible. Like, can we make is it possible to make like 4 candies per pile? That's going to be really hard for that helper function. But I think I'll include it just because these problems get kind of repetitive with the binary search part, so it's good to have some sort of challenge as well. But with that being said, I think I'll just throw this in as the last one. It's a great problem in general, in my opinion. So let's go ahead and talk about it. 1802, max value at a given index in a bounded array. So you are given 3 positive integers, n, index, and max sum. You want to construct an array, 0 index, that satisfies the following conditions. So they just give us a bunch of conditions. The num's length is going to be n. Okay, so the size of the array is n. Every element is positive. So something very important here. So positive means it's greater than 0, right? So it's 1 and above. The absolute value of nums I minus nums at I plus 1 is less than or equal to 1. In other words, this is just the distance, right? The difference between the neighbors just can only differ by at most 1. And the max sum of all the elements cannot exceed max sum. And what they want us to do is find nums at index where nums at index is maximized, right? That sounds kind of tough. And then, just returns nums at index. So I think it's better to actually go to an example. So let's just run through this example. When n is 4, let's just put this index at 2, and then the max sum is 6. Okay, so with an n equals 4, that means they're expecting some array of this size, right? And then if we just mark the indices 0, 1, 2, 3, they want us to return whatever index 2 would be maximized, right? So let's just say index 2 was like a 3. I'm just throwing out a random number 3. The key part is that the difference between the neighbors, right, cannot exceed more than 1. And if we don't want to exceed a maximum sum, it wouldn't make sense to increase, right? Having a 4 right here, and then maybe even having a 5, like that would only like add to our max sum, which might overflow it. So I think like thinking of it in a greedy manner, I think we always want to try to decrease, decrease, decrease. So this 3 would actually, to the left and right of it, would be 2. And then everything like anything outside of that would just be -1 as well. So this would be a 1, right? So this would be like a greedy way of filling in this array, but let's look at the sum. 3 plus 2 plus 2, so that's already 7, plus 1 is 8. And you see how this sum is 8, but 8 is too big than our max sum. So 3 will actually not work, right? So it's kind of tricky. There's a lot of like things to consider. But I think it's still the same where you could draw parallels to the last problem where we still have some sort of like possible answer, right? And then we also have like whether it works or not, right? Like does 1 work? Does 2 work? Does 3 work? Does 4 work? So on and so forth. And then we would have like true. In this case, the output was 2. So it would be true, true, and then false, false, false. And then everything after that would be false, right? There's the similarity in questions, but the reason why I chose this one is just the actual is possible is hard. So yeah, let's do that. Let's put a 2 right here for, let's just say. And then we always want to decrease, right? So over here it'd be 1, and then we can't decrease to a 0 just because, remember, every element has to be positive. So we can go to 2, but that would be weird, right? We would never want to add to our sum more than we have to. So it would just stick at a 1. Now let's sum all this up. 1, 2, 3, 4, 5. So this gives us a sum of 5, which is actually less than our max sum of 6. Therefore, 2 would work, right? Similarly, I don't know if it's obvious, but if we put a 1 right here, it would work because that's a 4, and 4 is less than, right? So same idea as the last one, we just want to find the first or the last occurrence of true. So let me just go ahead and code that idea, right? So we just have a helper function is possible. That's going to take some sort of possible answer. And maybe that's the index value, right? The value at this index, just see if it's possible. It's going to return a bool. And then now we could just do the actual binary search part of this. What's our left? What's our right? So this is very problem specific, and let's think about this for a bit. Remember, okay, num's I must be a positive integer. So again, left cannot be a 0. It has to be positive. So it needs to be at least 1. They want maximized. So let me see. I guess a maximized thing would be just doing the max sum, right? Because I'm thinking of what if there's only one element, then the max sum would be 6, and then that would be the answer right there. So other than that, max sum wouldn't work. So that would be our right bound, would be max sum. Our result, so yeah, so it's always possible that there's going to be some result. So I'll just put it as none for now, but it will be filled in for sure. Because we could always fill it in with 1, right? Because they say n is less than or equal to the max sum. Yeah, so they're not going to give us any bad inputs, is what I'm saying. So while left is less than or equal to right, find the mid, which is left plus right minus left divided by 2. If is possible at mid, res mid. Remember, just because it's possible. Oh, this is a little bit different. We want, oh, actually, no, it's the same. It's the same, sorry. So if it's possible, we still need to look to the right because maybe there's an even better answer. So that means left is equal to mid plus 1, right? Otherwise, it wasn't correct, so we need to look to the left. So right is mid minus 1. We just return the res when we're done. And we're done with the like meat and potatoes of this problem, as in like the binary search. This video is about binary search, right? We're done with that. But here's the like kind of crazy part is that calculating is possible. So this was tricky for me and I want to go through this. Okay, so one way or how I initially started solving this problem was actually to literally create an array, or not really create an array, but do something in linear time, right? Where I started at the index, and I guess I drew it out here. It's like I started at the index, and then I kind of just expanded going left and right. Like I had 2 pointers starting at the same spot, and they just keep going all the way to the ends. And every single time, just, doing one less than the last thing. So it would be like this would be a 6, and then this would be a 5. And then as well, like just making sure that these are all less than the max sum. And you can try doing that. I'm not going to do that now just because it didn't work, right? I got time limit exceeded. Max sum is 10 to the ninth. So even though I had an n log n time complexity, that just wasn't enough. Which means we have to do better than n log n. And what ended up happening is this is possible function needs to pretty much be constant. It needs to just be constant. And the time complexity that is acceptable is just log n. Okay, so what does it mean that how can I check to make sure if I can use something in constant time? Well, you could kind of get some hints that there definitely needs to be some sort of math involved, right? Because if you're not looping through the array, you're definitely going to have to use some sort of math. And if you just took a step back, that actually doesn't seem that bad, right? Because we know like in a greedy manner, if we're starting at 7, let's just ignore like the right side. Let's just look at the left, for example. So if we are doing things in a greedy manner, we always want to decrease until maybe we're at the very end and we have to use a bunch of ones and we have to pad our result with ones. Doing this whole like decreasing thing, decreasing by 1, we can kind of use the summation, right? Like the sum of I to k, I to n, it would be n times n plus 1 divided by 2. Right? Like we can do this to solve our problem. But what this does is it does 1 plus 2 plus 3 plus, all the way to n. And maybe that might not be what we're looking for per se, just because, take a look at this example, we had 7 plus a 6 plus a 5 plus a 4, and we stopped there, right? Even though the summation will include plus 3 plus 2 plus 1. And remember, don't look at the right side for now. We're just looking at the left. So what this means is that we kind of like, sure, we can take the, I'm just gonna call it sum with two m's. Like we'll take the summation of 7, but we also want to subtract it by the summation of 3, right? And that's the whole math part. If we do this, we are essentially canceling out this extra counted sum, and we are really just getting 4 plus 5 plus 6 plus 7, right? So that's the whole idea of what we're doing. But let me make another example of what happens when our indices are 0, 1, 2, 3. And now, okay, I'll do this. And let's just say we want this index at 4. We want to see what the max is. And let's just say is possible is a, let's just give it a 2, right? In this case, we can't do this whole summation thing because let's build it out in the greedy way where to the left of it is now going to be a 1. And then to the left of that, it can't be a 0 because remember, nums at I must be a positive integer. So we just need to keep it the same as 1, same at 1, same at 1. So we did use the summation formula, but we only used it this much, right? Because this is the sum of 2. So now that we have the sum of 2, we're not done. We still need to add, right? We still need to add this many ones. And how many ones is that? That's the index, which is 4, minus the index's value, which is 2, plus 1, which is going to give us 3. So this is how many additional ones that we need to use, which is going to be the index minus the index's value plus 1, plus the summation of 2, and that's going to give us 6. And that's kind of tricky. So just to like write it out one more time, we're really expecting two cases here. The first case is if the index value is greater than the index, right? Because if the index value is greater than the index, just like this one, then we're going to do this whole like summation thing. Then we're going to do the summation of the index value minus the summation of the index. And just to double check, is it greater than or equal to? I'm not so sure. Let me look. So if these are the indices and we had a 3 and it was 3, 2, 1, but then we need to pad it. Okay, so it needs to be strictly greater, like a 4, right? Once we have a 4, 3, 2, 1, then we can subtract by, then we subtract by the summation of 4 minus 3 minus the index val minus index minus 1, right? So this is what it means if the index val is greater than the index. We need to get the summation of index val minus the summation of the index val minus the index minus 1. So we remove the double counted is what I'm saying. The second case is just the opposite, right? Is the index val is less than or equal to index. So in this case, we're not over counting, right? See, we're not over counting if we use the summation, but we're under counting because there are padded ones that we need to take in account for. And you see index val is 2 and it's less than or equal to the index. So what this means is we definitely need the summation of index val. So I'm going to go ahead and do that. Summation of index val. But we want to add it with the index minus the index val plus 1. That's how many ones we need to pad it with. Index minus index val plus 1. Cool. Now, what did I draw here? This is the sum of one part all the way to the index, right? I guess this can be called like get sum given an index value as well as given an index. And it will return the expected sum. So I haven't finished the problem yet, right? Like if we are at this current index value, let's just call it like this current index, and it has a current index value. Let's get the sum of everything to the left and the sum of everything to the right. And then we can add it to our current index value to see if it's greater than the current sum, right? So to do that, we can actually call get sum, but what would we pass in for the index value? We would pass in the current index value minus 1. That's going to be our index value. And then our index would just be index minus 1, right? Like so. Because we're doing everything on the left side, not including where we currently are. So for the right, it's kind of like symmetry, right? Because if this was like a 5, this was like a 4, 3, 2, then we also see a 4, 3, 2 over here. But it might have ended early or whatnot. All we need to do is take the length. So we're definitely going to call get sum again. The index value is just going to be the index value minus 1. That goes unchanged. But now I'm just trying to think about what is a good index to pass in. And that would be n minus 1 minus I minus 1, right? That's just kind of like flipping it over. And once we have all of these, let's just call this like this is the left, this is just the original index value that we're checking, and then this is going to be our right. If we sum this up, we just need to return whether the sum is less than or equal to the max sum. So that's just going to be how to do it. And doing all that, these are just math operations, is just going to be constant. So it's possible I'm going to have some sort of like left sum and some sort of right sum. And I guess originally we could just set these as 0. It's possible that the index is all the way to the far left. So our left sum, we don't want to like call anything out of bounds. So I just want to make a check. If index val is not equal to 0, go ahead and set our left sum to, let's just call get sum with iv is the index value minus 1 with an index, right? Similarly, it's time to fill in the right sum, but we don't want the very end because there's nothing past that. So if the index, sorry, and this is the index, right? Not index val. If the index is not equal to n minus 1, then we can go ahead and call right sum, get sum, passing in index val minus 1. Oh, sorry, really quick. This is index val minus 1 with an index minus 1, right? So I'm just following this. And for this get sum for the right, it's index val minus 1 with a n minus 1 minus I minus 1. And then all we need to do is just return the left sum plus the index val that we're checking plus the right sum, whether it is less than or equal to the max sum. Cool. Now we just need to create def get sum. It's going to be given an index value as well as an index. And remember, there's these two cases we need to check. If index value greater than index, then we just need the sum of index val minus the sum of index val minus the index minus 1. Otherwise, and then we're just going to return this, right? Otherwise, we return something else, so I could just put a return right here. Now I'm looking here, we just return the sum of the index value plus, here is where we pad the ones, right? Index minus index val plus 1. So you see, I keep calling this sum, but I didn't create that either. And that's just going to be like the summation, the geometric series or whatever that I did up here. So def sum, it's going to take a value. It's going to return v times v plus 1 over 2, right? And just to be explicit, these are going to be ints. That's the sum. And then for the summation, it's also going to return an int. And let's just run this, see what happens. Right, sum is not, name I is not defined. Oh yeah, so this should be index, right? Awesome, so that ran. Let me go ahead and submit. Cool. Yeah, so if you watched to the end, thanks for watching. This last problem, it didn't have much to do with binary search. I mean, like this whole idea gets repetitive. I think the hard part, and I don't think I explained it that well, is using math to find something. But I really like this problem. I thought it's quite challenging, and I still didn't explain it that well. But yeah, I mean, this sums up the whole idea of binary search. We started with talking about what binary search is and just like how to implement just like the most basic form of binary search. And we kind of expanded that to try to tackle problems where binary search wasn't even obvious at all, right? Like reading this, you don't know to use binary search. So if this video helped you at all, please let me know. If there's anything you'd like me to do better on, please let me know as well. And yeah, thanks for watching.